Hello, this is Dr. Ali Mughibel. We're looking at spread spectrum signals for digital communications. This is part 1. We'll start with a quick introduction. In spread spectrum, the bandwidth W, the bandwidth of the signal, is much greater than the information rate. So the transmission bandwidth W is much greater than R, which is the data rate. So if we want to express that, if we compare W with the rate, we'll get a number that's much greater than 1. So this is called the bandwidth expansion factor. If this was passband communication, then the symbol rate and W would be the same and we get 1. But because we are doing spread spectrum, W over R will be expanded. And the measure of how much is W over R is called B, or the bandwidth expansion factor. But how do we increase the bandwidth? By redundancy. Redundancy is introduced to overcome the interference. So we are going to add extra data, redundant data, or redundant information. And that's done in radio and satellite communication. The best way to do it is not just to repeat the data, but rather to use coding. Coding is an effective method for introducing redundancy. Rather than the basic repetition code, which is not efficient, we'll use coding techniques to increase the redundancy. So we would like the signal to look like pseudo-random signal that appears like noise and are difficult to receive by the non-intended receivers. So instead of having, if you look at the spectrum, and the magnitude here is this F frequency. In case of narrowband communication, you have a peak in the spectrum which give a hint to the non-intended receiver that there is a signal here. As we increase the bandwidth, then we spread the bandwidth, then the power level goes down, and so the same amount of power need to spread. This is not the same scale though. And that will make the signal look like noise instead of being sharp in the spectrum. The major applications for spread spectrum includes compacting, jamming due to other users, or suppression of interference or jamming due to other users or due to self-interference. So we have different possibilities here. Either you compact jamming, or you suppress jamming or interference. And this could be to other users or due to self-interference. Self-interference is when the multipath component interferes with the signal. You want to avoid that, and possible solution for that is spread spectrum. Spread spectrum is also used for covert, hidden, secure communication privacy. And remember that in secure communication, you don't want the unintended users to know that you are communicating. Not just not being able to find the information, that's called information security. We're going one step over that by trying to ensure communication security. Spreading the signal can be very long. Spreading sequences, the added redundancy can be very long, which enable low transmitted power probability of detection, PST, low transmitted power spectral density. And then, of course, we got low probability of being intercepted, LPI. Especially, this is important in military communication. An example of that is CDMA, coded division multiple access. We have time division multiple access, frequency division multiple access, and now we have coded division multiple access, CDMA. And if you go back to history in communication, you find that was proposed as a solution for mobile future communication, but it did not fly, and that's called Qualcomm lie. There are some papers, interesting paper that says it's good, and then it's not good, and it's good. So during the history, CDMA was proposed as a solution. Although now 6G and 5G, they don't rely mainly on CDMA. You have TDMA and frequency and FDMA, and there could be some application, but they're not the main framework. CDMA allows multiple users to simultaneously at the same time use a common channel for transmission of information. The difference between the user is not time, is not frequency, but rather in the code itself. The key at the receiver would be to have the proper code to receive the signal. Fourth application is in radar. Spread spectrum is used for time delay, velocity, and ranging application to find the delay, for high resolution, to find the velocity of objects, and for ranging, finding the distance. How teleoperators market CDMA? How did they claim that it's going to be the future? Why people believe it's going to be the future? Because they promised higher coverage by going to 400% of GSM, what TDMA and FDMA can support. They claim the capacity, number of users, the cost would be reduced, clarity of the talk, and also the choice of having mixed communication between voice, data, and fax and SMS, and that is customer satisfaction. All these were promises, and you can see that this is already back in history. But this gives us a lesson of how to improve our prediction of what comes next. The most solid foundation for attracting and retaining subscribers is based on CDMA. So they claim that customer will be satisfied more with this technology. This is from Samsung Narrowband CDMA Marketing 2001. So we should learn from this lesson and do not repeat this again. Multiple access, we mentioned that we have frequency division, multiple access, TDMA, and now we have CDMA, where the entire time is all used by all users, frequency by all users, but the power is usually reduced spread of the signal for all. So FDMA, TDMA, and yield conceptually the same capacity. However, in wireless communications, TDMA has improved capacity to the following reasons: statistical multiplexing and graceful degradation. So it allows you to have more users with somehow similar codes to some extent, so you can have more, cover more users, but of course at the cost of quality. That's the theoretical expectation. And the performance can still be improved by adaptive antennas, multi-user detection, forward error control, and multi-rate encoding. So let's compare FDMA, TDMA, and CDMA. TDMA allocates time instant frequency, and we have a code for users. CDMA systems can be synchronous or asynchronous. So which means in synchronous CDMA, it's difficult to apply in multipath channels, that because you are going to assume that I'm going to send a code. This code is different between different users, but for a given instant of time. Once there is an overlap, once there is a shift or multipath, then this orthogonality could be destroyed. There might be some similarity once we have a shift. Therefore, in wide CDMA, as in ICE95, CDMA 2000, and wide CDMA, and IEEE 802.11 users are asynchronous, which means we cannot guarantee that the data will be received at the same time. So in general, we can classify the code as being orthogonal, and you might have heard about this name, Walsh code, or for orthogonal or near orthogonal systems, or we have near orthogonal and non-orthogonal codes like gold codes for asynchronous communication, and we have maximum length codes for asynchronous systems. Coverage objectives. Would like to cover the following. We have types of spread spectrum, direct sequence spread spectrum, and that's using PSK, QPSK plus pseudorandom noise. We also have that looks like a frequency hopping spread spectrum, FHSS. So remember, we have two main types, DSSS or DSSS, and we have FHSS. So we'll look at MRE, frequency shift keying plus pseudorandom sequence. And then we have the pseudorandom sequence will adjust the frequency that we select. So we have PSK, QPSK, that's for direct sequence. And then with frequency hopping, we'll be using frequency shift keying. And that will be explained in a second. We also would like to look at anti-jamming AJ performance for the CDMA, because we mentioned that one of the important usage for CDMA is anti-jamming. Okay, examples of direct sequence spread spectrum. In direct sequence spread spectrum, we have the following. We have data and we have a key. So this is the data 1101. So this is about 4 bits. Now the key is of course at a much higher rate, which requires more bandwidth. So what we are going to do here, we're going to multiply the key with the data. So this is, we get positive, okay, 1 times 1 is, so 1 times 0 is 0, 0, 1 times 1 is 1. So you multiply these two or you XOR them. So you get 0, 1, and so on, so forth. So for example, here we have 1 times 0 is 1 XOR. So you get 1, 0, 0, 0. Then we have 1, 0. So this is the data key. So this is the data key. The data XORed with the key now. Then if you XOR the two together, you will get 1 XOR 1 is 0. And then we have 0 XORed 1 is 1. So this is the data with the key. You can see that this was very low, and now we have a higher data rate. The second user is user B with 4 bits, and he has a different key. That's the key, and the data XORed with the key, and then we have now the signal B. Now if you add the two A and B together, you get the following waveform. Okay, so it could be if you add the two signals together, you get 0, 1, or minus 1. That's in the channel. So if you are going to look at the equivalent local signal, local key, so we have we're using the key with polarity. So now we're going to XOR or A plus B, the channel, with the data itself. So now you're going to multiply them, and you get the following sequence. So if you look at the integrator output, you'll find out that this is going to be negative mostly. This is negative mostly. This is positive. This is negative, and we have recovered the data back 0, 0, 1, 0. That's the comparator output for the case of the data. That's the inverse. That's just the inverted signal here. However, for the frequency hopping, what we do, we are going to divide the frequency axis into big slot.